start the recording again. So hi, now we are moving to the second part of the session. We have covered the errors part, and now we are moving to the measure. We are going to discuss mainly about the measuring instruments, right? Measuring instruments. Fine. So before that, some of you have asked about the details of the class, our main theory classes, how the plan is going, how we are working on the classes. Also, they have asked about the exams, though the paper classes I conduct. Yeah, the plan is from, I told you the date, right? From 11th Saturday, 7 p.m. to 11 p.m. We start mechanics from this day, and on every Saturday, 7 to 11, our classes, we are conducting our classes, the English medium 2028 class, starting from mechanics from this day, right? In every Saturday, we have the class at 7. And also we have paper classes. The paper classes are completely free for the students who come for theory classes. You don't want to worry, but we are not going to start paper classes now, right? Because if if we start paper classes, I have to give papers from your O levels, right? Because you haven't learned much more content in A levels, right? So normally we are starting paper classes like at the end of mechanics, right? At the end of mechanics, we start paper classes. So then you can join for those paper classes also. Those are also online. This class also totally online. You can join for entire 2.5 years online for the class. And after some time, we will move for 2 sessions for a week to rapidly cover the syllabus. We have a plan to cover the syllabus very quickly. I will explain those plans later in the class, right? Those are the plans. You can join and visit, right? The first day you can join freely, right? For the mechanics, first day you can join freely for the class, and after that you want to do the payments and all the details and the class fees. I will add to the group. For the first day you can join freely, right? This is about the class details, and the ones who want to join the class, put a message as 2028 EM to my WhatsApp number. You have my number, but I will write it again. Not 71465431, right? Put a WhatsApp message to this number as 2028 EM. We have single medium classes also. The single medium class is starting from this Sunday, I think 5th of Sunday, right? 5th or 4th. Yeah, 5th of Sunday, the same time, 7 to 11, right? From this Sunday onwards, the single medium classes are commenced, and from next week, next Saturday onwards, the English medium classes are starting. So also inform your friends if they are doing single medium, right? They can also join the session. And also for the single medium students, I did a complete seminar of measuring instruments of 6 hours, and it's in my YouTube channel. If you want that, also them let them know to drop a message to this number, and I will give the recording, right? Okay. And also, I haven't told you anything about myself, right? You know my name, right? I am Thusith Herath. This T-shirt also belong to my department. I'm in University of Moratuwa in Computer Science and Engineering department, right? In the engineering faculty, Computer Science and Engineering department. In the 4th year undergraduate, as a 4th year undergraduate, I have only few months to complete the degree. Mostly in June, I am completing the degree. And that's it, right? If you have something else to know about me, Please ask and I will tell. Right, okay. So, right. Some have joined newly also, I think. Let's move to the measuring instruments part now. We have completed the errors. If you have missed that errors part, you can watch the recording later. I will upload it tonight and send you the links, right? Okay. For when we talk about the measuring instruments, I told that there are 5 instruments to learn: meter ruler, vernier caliper, micrometer screw gauge, spirometer, and the traveling microscope, right? 5 instruments: meter ruler, vernier caliper, micrometer screw gauge, spirometer, and traveling microscope, right? These are the 5 instruments we are going to learn. Out of them, vernier caliper and the traveling microscope is based on the Vernier principle, right? Still, you don't know what's meant by the Vernier principle, but we will discuss about it now. But you have to know that the Vernier caliper and the traveling microscope is based on the Vernier principle, and the micrometer screw gauge and the spirometer are based on the screw principle. And these two based on Vernier principle, right? What about meter ruler? There's nothing. Nothing is based to build the meter ruler, right? Meter ruler is the meter ruler. Right. So first we are going to discuss about meter ruler. Okay. Let's move to the part topic meter ruler. And there's a diagram of meter ruler. Here there's a box containing all the important details about meter ruler. First one, least count 1 millimeter, you know. Measuring range, you can measure from 0 to 100 centimeters using meter ruler, you know it. The minimum length that can be measured without exceeding 1% percentage error, you know it. That's 10 centimeters, right? That's 10 centimeters. Here, you can write in front of that 10 centimeters as that this 10 centimeter value is obtained by multiplying the least count by 100. Can you remember the calculation what we did in order to have a percentage error less than or equal to 1%? We have to calculate the percentage error. 1 millimeter should be divided by the measurement. We'll take it as x into 100 should be less than or equal to 1. That's the equation, not the equation, inequality. So x should be greater than or equal 1 millimeter into 100. So you can go for an kind of a pattern here. Always the least count is multiplied by 100 to get the minimum reading without exceeding the percentage error 1%, right? So here in front of 10 centimeters, you can write 1 millimeter into 100. Right? 1 millimeter into 100. Good. Okay. So about meter ruler, there is much. There are no much more content to learn because you know about meter ruler. It's a very simple instrument. There's a question. There's a problem. What's the problem? You are provided with a meter ruler to measure the thickness of a coin. Oh my God, it's a serious deal, right? You have to measure the thickness of a coin using a meter ruler, which is approximately 5 millimeters. Impossible, right? To measure 5 millimeters using meter ruler. Is it okay? Is it acceptable? No. You know that at least the length should be 10 centimeters to get it from a meter ruler, right? You know that. But now you have to measure 5 millimeters. How to do? Explain how you would obtain this measurement such that the percentage error does not exceed 1%. Oh my God. You have to take the measurement. You have to measure the value of the thickness of the coin without exceeding the percentage error 1%. And also there's a hint who have any number of coins, right? You have as many you may use as many identical coins as needed. You have much more coins as needed. So how to measure? Can anyone suggest a method to measure the thickness of a coin? Meanwhile, you have to stop exceeding the percentage error of 1%. Can anyone suggest a method? Can anyone suggest a method? Can anyone unmute yourself and speak up, suggesting the method? How we should measure the thickness of a coin, thickness of the coin. So what's the constraint here? The length should be greater than or equal to 10 centimeters, right? At least the length should be 10 centimeters, which is going to measure from the meter ruler. So the thing I can do is I can keep those identical coins one top of the other, right? Until I get the total height greater than 10 centimeters. Until I get the total height greater than 10 centimeters, right? Now, this should be 10 centimeters. Then I can measure this height. And then to get the thickness of a one coin, what should I do? If I have kept n number of coins here, I have to divide the measurement by n to take the thickness of a single coin. Got the point? Now you have you are okay with all the requirements. You have measured the thickness of a coin, also it's fine, and also you haven't exceeded the 1% error in the measurement, in the reading, right? Cool. So how to write this? This is the method, right? So how many how many coins will you need for this? For that part, they are giving the approximate thickness is 5 millimeters, right? Approximate thickness is 5 millimeters. Approximate thickness is 5 millimeters. So we will take the percentage error 1 millimeter over the measurement. Measurement is one coin is approximately 5 millimeters, and there are n number of coins. So the total measurement is 5 into n. Got it? One is 5 millimeters, and there are n number of coins. Then the total measurement is 5 into n. Least count over the measurement into 100 should be less than equal to 1. This is our inequality, right? So if we subject n should be greater than or equal to 1 over 5 into 100. Here the millimeters to millimeter will cancel off. 100 over 5 means 20. So we can write the answer as we have to keep more than 20 coins one top of the other in order to make the total length measurement greater than 10 centimeters. In order to make the total length measurement greater than 10 centimeters and measure this length, measure this height and divide it by the number of coins used. Got it? Right. Write this in the space. The ones who are writing in the tube, they can write this in the space provided, and ones who are writing in the separate papers, just put the number, page number, and answer this. Write this, draw this diagram and write this Then I will give some sentences about describing the way of solving the problem, right? Complete this part. Complete this part. I assume you have completed. Right here below the workout. Keep more than 20 coins. Keep more than 20 coins, one top of the other. Keep more than 20 coins, one top of the other. Keep more than 20 coins, one top of the other. Keep more than 20 coins, one top of the other. And measure the total height. And measure the total height of coins. And measure the total height of coins. Divide it by the number of coins. Divide it by the number of coins and get the average. Get the average value. Get the average value. Get the average value. Got it? That's the way you have to solve this problem. These are the kind of interesting problems you have to face in this physics, the journey of physics. To complete the journey of physics, you need logic. That's why logic of physics is here. Right? Completed. Right. Here, I need to highlight a point here. If you want to reduce the error, the percentage or the fractional error, you can do two things, right? If you want to reduce the percentage or the fractional error, you can do two things. The fractional error means the least count is divided by the measurement, right? This is the fractional error. To reduce this, you can reduce the least count. That's the one method. That's the one method you can use. Or you can increase the measurement because this is a fraction. In order to decrease the value of this fraction, you can reduce the upper part or you can increase the lower part. You can do both. Here, what we did is increase in the measurement. The approximate thickness of a one coin is 0.5 millimeters. You can't measure 5, so you increase the measurement. up to 10 centimeters. You did this part. Also, you can, this part means you can reduce the least count. So how to reduce the least count of the mean ruler? You can't reduce the least count of the mean ruler. You have to use another instrument which has a lower least count. Got it? Or sometimes in some instruments you can reduce the least count also, right? We will talk about them later when we come to those instruments. But in meat ruler, generally you can't reduce the least count. If you want to reduce the least count, you have to recalibrate the scale, right? Now it's calibrated from 1 millimeter to 1 millimeter. If you can calibrate it from 0.5 to 0.5, then the release count is reduced, right? But generally, if you want to reduce the least count means you have to select a separate instrument which has a lower least count, right? Great. We'll write this point as well in that space. Write this point as well right here. If you want to reduce the fractional or percentage error of a measurement, if you want to reduce the fractional or percentage error of the measurement, you can do two things. You can do two things. You can do two things. Number one, increase the measurement. Increase the measurement. Number one, increase the measurement. Number two, decrease the least count. Decrease the least count. Decrease the least count. Means that decrease the least count means that select a separate instrument. Select a separate instrument which has a lower least count. Which has a lower least count. Select a separate instrument which has a lower least count to get the measurement. To get the measurement. Right? So put that last sentence into a red box and highlight it, or whatever thing you can do to highlight that part, that sentence, right? Because that sentence is very important to write for right answers, to think about the problems. Okay, there's another question. What's that? You are provided with the meat ruler to measure the internal depth of a cylindrical container. Explain the possible error that may occur during this measurement and describe how to avoid it. Describe how to avoid it. Okay. You are provided with a meat ruler to measure the internal depth of a cylinder. Right. There's a cylinder. You have to measure the internal depth. How you going to measure the internal depth? Simply, you just put the meat ruler inside. Right. Then you get the reading here. Right. Using this scale, you can get the reading here. What's the error happens in this situation? Can anyone explain? What kind of a specific error? There's a specific error happens in these kind of scenarios. What's the error? Can anyone guess? Can anyone guess the type of error happening here? What's the error? What's the error? The error is if you mark the scale, the 0 mark will be here, right? So if here the reading is, let's take it as 140 millimeters. So is the internal depth of the cylinder is 140 millimeters? No, because 140 millimeters are marked from the 0. From here to here, there are 140 millimeters, but there's a gap between edge of the mid rule and the 0 mark. You have to measure this part also. This is the error happens. So what's the name of this error? We learned this. What's the name of this error? Parallax error. This is also a kind of parallax error because the edge of the measurement doesn't align with the scale lines. Edge of the measurement doesn't align with the scale lines. That's the parallax error we learned before, right? So the error happens here is the parallax error, right? In the space provided, there's a box. In that box, draw this diagram. Draw this diagram. You don't want to write this 140 millimeters. Draw this diagram. And in the diagram, clearly demonstrate that the 0 mark, there's a gap between edge and the 0 mark. Draw the diagram. Belong to that question. Right? Finished drawing, right? Write the answer. So they are asking, explain the possible error that may occur during the measurement and describe how to avoid it. So how to avoid it? Can you suggest a way to avoid this error? Can you suggest a way to avoid this error? How to avoid this? How to avoid this error? How to avoid this? A simple way. Put a stick to the vessel and mark the point here and measure the, or you can break the stick from here and measure the length of the stick separately using the mid rule. Simple. Got it? That's the way you have to think about the problems. Don't take them as very heavier problems. So they are very simple. Just take a stick and put that in the vessel and break it and measure the length of the stick separately using the mid rule. Right? Simple. Write the answer. Write the answer. If we going to measure the internal depth, if we going to measure the internal depth using the mid ruler, as in the figure, if we going to measure the internal depth using the meter ruler as in the figure, the zero mark of the meter ruler doesn't align with the edge of the measurement. Zero mark of the meter ruler doesn't align with the edge of the measurement. So it leads to a parallax error. So it leads to a parallax error. Next point. In order to avoid the error, mark the internal depth of the vessel. Using a stick. And measure the marked stick separately using the meter ruler. Separately using the meter ruler. Got it, right? That's the way you need to think about problems, how to solve problems, even not in your physics, even in your day-to-day life, right? Start thinking simply. The meter ruler is over, right? So let's move to the Vernier caliper. Vernier caliper. Okay. Here is a Vernier caliper. This is not a Vernier caliper used in industrial scale. This is a kind of a toy item. But you can understand the principle of Vernier caliper using this, right? You can see. First, you have to know that there are two parts of Vernier caliper, as you see. Here, there's a one part which is, I will keep it here. This part is at stationary, and you can move the other part along the stationary part. Right? This is the first thing you have to learn about the Vernier caliper. So before moving to Vernier caliper, let's first learn about Vernier principle. What does this mean? Go to the tute. The Vernier caliper is designed based on the principle of Vernier scale. Therefore, we will first focus on Vernier principle. It has two scales, yeah, the main scale and the Vernier scale. Vernier scale can be slight against the main scale, as you can see here, right? So this is the Vernier scale. It can be slight against the main scale. The main scale is here. If you can see this, now you can't see, right? Fine, it's fine. Also, I will show you a simulation of this Vernier caliper. Let me share my screen. Give me a second. Okay. Here's the simulation of the Vernier Caliper. Here you can see. You can move this part along the main scale. So here is the main scale. So I annotate on this. Here's the main scale, right? And how to select colors here? Right here. And so this should be the Vernier scale, right? This one. You can slide the Vernier scale along the main scale. Okay. Consider then the next part. Consider a Vernier scale in which 9 1 millimeter divisions, right? You can put a comma after the 9. 9 1 millimeter divisions. 9 1 millimeter divisions of the main scale are divided into 10 equal parts on the Vernier scale, right? So I will draw the Vernier scale. There are 9 1 millimeter parts in the Vernier in the main scale, right? Consider Vernier scale in which 9 1 millimeter divisions of the main scale are divided into 10 equal parts. The Vernier scale is made up of dividing 9 1 millimeter parts into 10 equal parts. So in the main scale, there should be 9 millimeters then. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And 10 is there. But the Vernier scale is produced by dividing 9 1 millimeter parts into 10 equal parts. So, what will be the value of one Vernier scale part? Let's try to figure it out. Vernier scale is made by dividing 9 1 millimeter parts. So, the 9 1 millimeter part means 9 into 1 millimeter into 10 equal parts, right? This is the length of a one Vernier scale part. So it should be 9 or 10 means 0.9 millimeters. Means that one Vernier part is less than 1 millimeter. So I will start drawing Vernier scale. So 0 should be here. And first Vernier line should be 0.9 millimeters apart from the 0 line. So it should be like here. Here's the first Vernier line because length of a Vernier part is 0.9 millimeters. The second Vernier line should be 0.9 millimeters from here because every part of the Vernier scale should be 0.9 millimeters. So 0.9 millimeters from here, here's the first line, and the second line should be 0.9 millimeters from here. It should be like this. Then third one, 3, fourth one, 4, fifth one, 5, sixth one, seventh one, eighth one, ninth one, and 10th one should be coinciding with the ninth line of the main scale. Correct? Yes. Initially, we told that 9 main scale divisions are divided into 10 equal parts. Got it? Yes, got it. Got it, right? Here you can see the gap between the first vernier line and the first main scale line is 0.1. If we go to the second line, it should be 0.2, right? Because 0.9 millimeters and then 0.9 millimeters, it's 1.8. Here 2 millimeters. So if we reduce 1.8 from 2, it's 0.2. Like that, you can see the length between the relevant lines is increasing, right? There's a more length difference between 3 and 3 lines, much more difference between 4 and 4, and much more between 5 and 5, right? And go to the end, there's a 1 millimeter gap between 10 and 10, right? So if we write down the gaps here, right? The distances between main scale and vernier scale is the distance between main scale and vernier scale lines. So here I take capital M for main scale, V for vernier scale. So this is the main scale, this is the vernier scale, right? Distances between M and V scale lines. So 1 M and 1 V, what's the distance? This is 1 millimeter and a vernier part is 0.9 millimeters, so this should be 0.1. 2M and 2V, what should be the difference? Here 1 millimeter plus 1 millimeter, it's 2 millimeters. Here 0.9 plus 0.9, 1.8. If we reduce 1.8 from 2 millimeters, it's 0.2. So guess and put in the chat. What should be the difference between 3M and 3V? Quickly put in the chat. What should be the difference between 3M and 3V? 1 millimeter, 2 millimeter, 3 millimeter. Here 0.9, 1.8, 2.7. Then what's the difference? 3 minus 2.7 means 0.3. Good. So now I want to answers. Guess and tell what will be the difference between 8M and 8V. What's the difference between 8M and 8V? What will be the difference? 8M and 8V. What's the difference? What should be the difference? 8M and 8V. What should be the difference here? 0 point, how much? What should be the difference of 8M with 8V? Give me the answers. Yeah, good, good. Quickly, quickly, quickly. Quickly put into the chat. Don't think as that guy has already put the answer, so I don't want to put. No, you want to put, because I told earlier the purpose of putting answers in the chat is to engage you with me. So you have to engage. So quickly put the answer. What should be the distance between 8M and 8V? It should be 0.8, right? Good. So 9M and 9V, 0.9, right? 0.9. So 10M and 10V, what should be the value? What's the difference? 10M and 10V, you can clearly see that it's a 1 millimeter difference. There's a 1 millimeter difference between 10M and 10V. So 1.0 millimeters. Got it? Okay. Draw this in the provided space in the box and complete this. Complete this part. Within the box, also write the length of a vernier part. Length of a vernier division. Also write this workout within the box provided to draw this, right? Draw this as well as write this within the box and complete the distances between M and V scale lines. Quickly complete it. When you are drawing this, do it more accurately, right? The gap between the relevant line should be increasing gradually, right? Okay, complete it, and after completing, put done to the chat box. After completing, right? After completing, drawing this, writing this part within the box, and also completing this, the distances between main scale and Vernier scale lines, put done to the chat. Put as done. 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 Everyone completed? Okay, right. I assume that everyone has finished. So for the last time, put done everyone to the chat who has finished. The ones who have already put, don't want to put again. Other ones who have finished drawing and writing this all stuff, put done to the chat. Because then only I can identify you have finished or not, right? So because therefore, engage with me for the all members, because if you are always not sending any responses, I assume that you are not in the seat. Right, good. I think, I assume many of you have completed, right? Okay, for the next part, then I am moving for a separate, another explanation. the distance by which vernier scale must be slide to coincide with the line in the main scale. So, as you all know, as you all seen before, the vernier caliper, you can slide the vernier scale on the main scale. So, how much you want to slide this in order to coincide a vernier line with the main scale line? The distance by which vernier scale must be slide to coincide with the line on the main scale. So the next part. For that, 1m and 1v, you need to slide 0.1 millimeters. 2m and 2v, 0.2 millimeters. 3m and 3v, 0.3 millimeters. Same workout, right? You want to slide the vernier scale on the main scale from these two distances in order to coincide a vernier scale line with the main scale line. Got it? So here's the point. Here's the interesting point. What's the minimum amount that can be measured from this vernier scale? What's the minimum amount that can be measured from this vernier scale? That is 0.1 millimeters. Why? When you are sliding the vernier scale to this side, if first vernier line coincides with the first main scale line, you know that the vernier scale has pushed 0.1 millimeters. That means you have measured a length of 0.5 millimeters. Got the point? So here, the way you are getting measurements is you have to put something inside these two jaws and read the measurement from here. So if here the measurement is, let's take that 10th vernier line is coinciding with the 10th main scale line, then you have moved this vernier scale 1 millimeter to this side. Means the measurement is 1 millimeter. Simple. So the minimum measurement you can obtain here is 0.1 millimeters. So let's guess and put in the chat. So what should be the least count of this instrument? What should be the least count of this instrument then? Put in the chat. What should be the least count of this instrument? It should be what? Then what should be the least count? Least count is the minimum amount that can be measured. The minimum amount that can be measured from this instrument is 0.1 millimeters. So the least count should be 0.1 millimeters. Got the point? You have to write this again, right? Again, as the tute itself, there are spaces to write only the answers. But for the ones who are writing in papers, they have to complete it again. The sentence should be here is in the tute, the distance by which the vernier scale must be slide to coincide with the line on the main scale. Complete, write the sentence and complete this again. Which is on the top of the A9 page. Right, you have completed, I guess. So accordingly, the smallest value that can be measured with this vernier scale is 0.1 millimeters. So, sir, can you again briefly explain how we measure using the vernier scale associated with the main scale, right? We can slide the vernier scale along the main scale. Fine, got it. So as you also can see in here, you can slide the main vernier scale on the main scale. Okay. Here is a view of main scale and the vernier scale. If you slide the vernier scale by 0.1 millimeters, means if you put some kind of a wire or something that is 0.1 millimeters, it looks like this, right? It looks like this. So if we do this, if the length of this wire or the diameter of this wire or something is 0.1 millimeters, the first line of the vernier scale should be coincide with the main scale line, right? So inversely, looking at the scale, if the one is coinciding with main scale one, you know that vernier scale is slide an amount of 0.1 millimeters. Then you can guarantee that the measurement is 0.1 millimeters. Got it? Did you get the point? Thank you. Right. So the least count of the instrument is 0.1 millimeters. Then the topic, least count of a vernier caliper. Least count, how to find? Least count of a vernier caliper is the minimum distance by which its vernier scale must be slid to coincide with a line on the main scale. Minimum distance that the vernier scale should be slid in order to coincide with the main scale line. Here the minimum distance is 0.1 millimeters. That's the least count. So there's a space to work out that. I will work out it again. How to work out it again? Here's the general way of finding the least count of any kind of vernier caliper. Here for the example, we'll take the above scenario again. Here, one main scale division is equals to 1 millimeter, right? One vernier scale division is equals to how much? 9 1 millimeter divisions are divided into 10 equal parts. Then 1 millimeter into 9 should be divided into 10, means 0.9 millimeters. After finding the length of one main scale division and one vernier scale division, you have to draw it. How to draw? You don't need to draw the entire vernier caliper. Zero line, first line. This is the main scale. And the vernier scale, zero line, first line. So you know that main scale division is about 1 millimeter. So this length is 1 millimeter. Vernier scale division is about 0.9 millimeters. So this length is 0.9 millimeters. So the minimum distance is this much. This is the minimum distance you want to slide the vernier caliper, vernier scale on the main scale to coincide with the line of the main scale. So least count equals this 1 millimeter minus 0.9 millimeters. Really, the least count here is the D. D is the least count, the minimum distance that the vernier scale should be slide in order to coincide with the main scale line. Here the answer is 0.1 millimeters. This is the general way of finding the least count of any vernier caliper. Find the length of one main scale division, length of one vernier scale division, draw a diagram showing that length and calculate the minimum distance, right? Complete this. Complete this. Here the zero mark should be aligns with the zero mark. Zero line of the vernier caliper should be aligned with the zero line of the main scale line. Complete. Draw the diagram in the box and complete the workout. Complete it. Right, I assume that you all have completed. So there's also a short method to do this as well. What's the short method? A short method to find the least count of a Vernier caliper. So you have to memorize this the long way, right? This is the fundamental of finding the least count, right? You have to memorize this part. But for MCQs and sometimes you will need a short method. What's a short method? You can divide least count equals length of a main scale division over number of vernier divisions. Length of a main scale division, the equation is in your tute, right? Length of a main scale division is 1m over number of vernier divisions, number of v. Let's put this and check whether it's correct or not. Length of a one main scale division 1 millimeter. Number of vernier divisions 10, right? So the answer is 0.1. Yeah, it's correct. Write this as well. The equation is in the tute. You can complete the tute later after you get a printed copy. And in the tute, the equation is there. You can complete the next two rows, right? In the tute, you can work out the last two rows of the workout. Right. Got it. Okay, so after completing everything here, put into the chat that did you understand the way of finding the least count of the vernier caliper? Put yes to the chat if you understand the way of finding the least count. Put yes to the chat if you got this point. Yes, yes, yes. What about others? Yes. Some are missing in the chat. Okay. Okay, good. So we are going to do some more examples here. So for that, I will go for the iPad, right? I will share my iPad screen with you, then it will be easy. Let me share my screen. Okay. Now, you will be able to see my screen. Okay, right? You can see my screen clearly, right? Okay. So now, let's go to this question. A vernier scale is made by dividing 19 divisions of the main scale, each 1 millimeter into 20 equal parts. So I will sit on this chair and complete, right? 20 equal parts on the vernier scale. Find its least count. Right. Let's work out on this. What's the method? What's the sequence? First, find the length of a one main scale division. It's 1 millimeter given in the text, given in the question. What is the length of one vernier scale division? 19 main scale divisions are divided into 20. So 1 millimeter into 19 divided by 20. If I simplify this, 19 over 20 means how much? 0 for 19, then for 190, 190, 9, it's 180, 10 remains, for 100, it's 5. Right. So I have found the length of a main scale division and length of a vernier scale division. The next part is draw the diagram. Okay. Here's the main scale 0, main scale 1, and the vernier scale 0, and vernier scale 1 should be like this here. So the least count is the length of this difference, the length difference between main scale 1 and vernier scale 1. Here also I write this is the main scale, this is the vernier scale. So the least count equals 1 millimeter minus 0.95 millimeter. The answer is 0.05 millimeters. Got it? This is the correct way of finding the least count of this vernier caliper, right? Also, I will include the lengths here. This is 1 millimeter. This is 0.95. Right? This is the complete workout to find the least count of the this vernier caliper. Complete it with me. After completing, put done to the chat, right? Then I can identify whether you have finished or not. Then I can move to the next question. Done. What about others? Done, done. Done. Good. Okay. So then, right. Good. I will move to the next question. Here also you can see a diagram of this scenario, right? Here you can see there are 19 main scale divisions up to here are divided into 20 equal parts, right? 20 equal parts. Here you can see always a gap. There's a gap between 1 and 1, 2 and 2, 3 and 3, and the gap is gradually increasing. And finally, 20 and 20, there's a gap of 1 millimeter, right? Got the point. Let's move to the next question. Now, also you have to find the least count using the short method. Also try it, short method. I will do it in a circle right here. Least count equals 1 main scale division divided by number of vernier. So I don't write here. Main scale division equals length of one main scale division. It's 1 millimeter divided by number of vernier divisions. It's 20. So 1 over 20 means 0.05. Fine. Okay. Also write that short method also relevant to the question, and keep it in a circle or any kind of shape. Okay, let's go to the second question. The vernier scale is made by dividing 49 divisions of the main scale, each 0.5 millimeter. Here the length of a main scale division is 0.5 millimeters into 50 equal parts. Let's try. One main scale division equals 0.5. One vernier scale division equals 49 0.5 parts. So 0.5 millimeters into 49 are divided into 50 equal parts, right? So the answer is 0.5 over 50 means 0.5 over 10 means 0.01 into 49 means 49 means 0.49 millimeters, right? This is the length of a one vernier division. So let's draw zeroth main scale line, uh, first main scale line. Really the first means this is 0.5, right? Because main scale is calibrated, the scale is calibrated in millimeters. So the first line should be 0.5. Then the vernier scale, 0, and here the first line. Vernier scale lines are numbered from 0, 1, 2, 3, 4, 5, because there's the length is not shown in the scale. Only the 0, 0, 1, 2, 3, 4, 5 numbers are there. But in main scale, the lengths are there. This should be a bit below the 0.5 line because the length is 0.49. Here the length is 0.5 millimeters. So the gap between main scale line and a vernier scale line is, you have to reduce 0.49 from 0.5, means 0.01 millimeters. Got it? Yes. Let's check the short method. Least count equals length of a main scale division 0.5 over number of vernier divisions 50. 0.5 over 50 means 0.01. It's also correct. Got it? Complete the second question. Right. Everyone completed? I guess yes. Let's go for the next part, extended verniers. So without discussing much more about the topic, let's work out the question. Then you will figure out what does this extended verniers means. Okay. So here, a vernier scale division is made by dividing 19 divisions of the main scale, each 1 millimeter, into 10 equal parts, right? Length of a main scale division, 1 millimeter. Length of a vernier scale division, 19 main scale divisions are divided in 10 equal parts, right? So the length of a one vernier division is 1.9 millimeters. Now we have to draw the diagram. Main scale 0, 1. If we draw the vernier scale 0, where's the first vernier line? It's 1.9 millimeters, means it shouldn't be here. Because if it is here, it should be less than 1 millimeter, but it's almost 1.9 millimeters. So we have to draw the second main scale line also. And the vernier scale line should be in a position here. This is 1.9 millimeters. And this is, and the upper part is 2 millimeters. So what's the least count? we define least count as the minimum distance that the vernier scale should be slide to coincide with the main scale line. So here you can see, if you slide this by 0.1 millimeter, this 1 and 2 lines will be coincide, right? It doesn't want to coincide one with one. The definition is what amount you should slide the vernier scale on the main scale in order to coincide with the main scale line, the minimum distance. So here the minimum distance is 0.1 millimeter. It's gained by reducing 1.9 millimeters. So here the least count is, you have to minus 1.9 millimeters from 2 millimeters, and it's also 0.1 millimeter. Got the point? Always, if you want to understand this clearly, you have to draw the diagram, right? Then only you will get a better understanding about the thing, right? Let's work out the short method. Least count equals length of a vernier main scale division 1 divided by number of vernier divisions, it's 10. Again, it gives the correct answer, 0.1 millimeter. Complete it. So here you can see a difference between the above examples and this one. That's why these are called as extended verniers. Here the vernier scale are extended, right? That's why the name is given. Complete it. Okay, for the next part. A vernier scale is made by dividing 39 divisions of the main scale, each 1 millimeter, into 20 equal parts. Let's work out. One main scale division is 1 millimeter. One vernier scale division is 1 millimeter into 39 over 20. Now you know the scene. The answer is 39 over 20. Means the answer 19 remains 490. It's 9. 180, 10 remains 400. It's 5. Draw the diagram. Here also you can see that the vernier scale division is larger than a main scale division. So you have to go for 2 main scale divisions. Also, this is again the extended vernier. 0, 1, 2. In the vernier scale, it should be here, right? The first line of the vernier scale should be here. And this is 1.95 millimeters. So then the least count is 2 minus 1.95. Means 0.05 millimeters. Let's do the short method. Least count equals length of a 1 main scale division over number of vernier divisions 20. 1 over 20, 0.05. Again, it's correct. Complete it. Right. Next. Last question. This is not extended vernier. That's why I have separated this question from the above questions by a line here. So let's move to the question. A vernier scale is made by dividing 9 divisions of the main scale, each 1 millimeter, into 20 equal parts, right? One main scale division equals 1 millimeter. One vernier scale division equals by dividing 9 main scale divisions into 20 equal parts, means 9 over 20. The answer is 0, and for 90 it's 4, 10 remains. For 100 it's 5, 0.45 millimeters, right? Now it's fine, it's less than the length of a vernier main scale division, so we'll draw the diagram. Zero, 1. So the length of a vernier scale division is 0.45. 0 and 0.45 means it should be less than 1, right? Could it be here? No, it's wrong, because 0.45 should be even less than the half of a main scale division. If we take the half of the main scale division, it's also 0.5. 0.45 means less than the half of the main scale division. So 0.45, the first line of the vernier scale should be here, and the second line of the vernier scale should be here, right? So in order to coincide with the main scale division, now the second line of vernier scale division is going to coincide with the first line of the main scale. So the distances are here 1 millimeter. Here you can see 0.5 plus 0.5, 0.9. So the least count should be, you have to reduce 0.9 from 1. 0.1 millimeters. We'll go to the short method. Length of a main scale division 1 millimeter. Number of vernier divisions 20. 1 over 20. 0.05, right? That is wrong. That's totally wrong. For these kind of vernier scales, you see a difference of you see a difference between this one and older ones, right? We have mainly discussed 3 types of vernier scales. First one is one part is coinciding with the line 1 is coinciding with the first line of the vernier caliper. The second part, line 2 of main scale, is coinciding with the line 1 of the vernier scale. Here, first line of the main scale is coinciding with the second line of the vernier for these parts. So for these kind of questions, this short method will not work, right? So again, write the short method, then put a cross mark there. Complete all the questions. So you can't use the short method for the questions like this. There are several types of vernier scales, like there are circular vernier scales. Let's go for the circular vernier scales. Here it's also simple. The main scale is in a circular type, and the vernier scale also move in a circular path. You can move it like this, right? These kind of vernier scales are there in an instrument called spectrometer. So spectrometer. You will get into know about spectrometer in the lesson light, right? Until that, you don't want to go for much more details about spectrometer. You just want to know that there are kind of these circular vernier scales, right? So let's find the least count here. Here the only difference is these are not marked in millimeters. These are marked in angle, degrees, right? Because this is an angle. You can't mark an angle in millimeters. You have to use the suitable unit. That's degrees. Okay. Again, the same way. A vernier scale is made by dividing 29 divisions of the main scale, each half degrees, into 30 equal parts. Okay. One main scale division equals half degrees. One vernier scale division equals 29 such divisions, means 1/2 into 29, half into 29, such divisions are divided into 30 equal parts. So 29/60, right? This is the length of a vernier scale, vernier division. To make this more meaningful, I will convert this length of, not the length, the angle of one main scale division also as a factor of, as a multiplication, or the factor, or anything of 60. You can multiply the upper part and the lower part by 30, then you can end up with this as 60 or 30 over 60. Because now you can easily compare the main scale division with the vernier scale division, right? So now you can draw here. This is the main scale division, 0, and here the next one, it is half degrees. If I go to the vernier scale, I will erase this. If I go to the vernier scale, 0, and the first vernier line is 29 over 60, means less than half. It should be here. So now the least count should be 30 over 60 minus 29 over 60. Means 30 minus 29, it's 1 over 60 degrees, means 1 minute, right? 1 over 60 degree means 1 minute. You have learned about this in your O levels, right? Minutes and seconds. If we divide a degree into 60 parts, that is called a minute. Okay. So can you use the short method? Yeah. Least count equals angle of a one main scale division, 1/2, half, divided by number of vernier divisions, it's 30. So 1 over, so here you can realize that 2 goes to here. 2 into 30 means 60. 1 over 60 degrees. It's fine. Complete it. Complete it. Right. The next part. A vernier scale is made by dividing 14 divisions in the main scale, each half degree. One main scale division is half a degree. One Vernier scale division is 14 such parts are divided into 30. Means 14 over 60. Again, for the consistency, I will convert the main scale division, the degree of the main scale division also as a part of 60. Multiply it by 30. It's 30 over 60, right? Okay. We can draw 0 and half. The Vernier scale 0. Here you can see 14 over 60 means less than half degrees, like less than 1/4 even, because if it was 15 over 60, it means 1 over 4. 1 over 4. 1 over 4 means exactly half of this, half of half degree. But even less than 1 over 4 means it should be less than half of the main scale division. So you can have two Vernier scale divisions here and here in order to coincide with the main scale division. So 14 plus 14, here 1, 2. Here this angle should be equal to two Vernier divisions, right? It is 14 plus 14, 28, right? 28 over 60. If we multiply the Vernier scale division by 2. So now you can find the least count. Half minus 28 over 60 means 30 minus 28, right? 30 minus 28 over 60 means 2 over 60 means 2 minutes, right? It's 2 minutes. We'll test it by the short method. Least count equals angle of a one main scale division divided by number of Vernier scales. It's 30. It gives the answer as 1 over 60, right? But it should be wrong, right? It is wrong. Because this scenario is same as this scenario, the one we got wrong, the short method, right? So for those kind of scenarios, the short method does not work, right? Complete it. So this is the correct method. Right. Okay. So put yes to the chat if we have understood to find the least count clearly. Right? Put yes to the chat if you understood this clearly. Yes, yes. What about others? Put yes to the chat. Yes, yes, yes. What about others? Also, you can put no to the chat, right? If you haven't understand it correctly, put no. Yes, yes, yes. Okay, I guess all have understood it correct, right? Okay. Are you tired now? Are you tired? Do you want a break again? Do you want a break? Just put in the chat. If you want a break, I can give. If you don't want, we can continue. Some says no, you don't want a break. Others, what would you say? Do you want a break or no? Some have privately messages. They want a break. Okay, okay. I will give. Let's have a 15-minute break, right? Don't quit the Zoom. Be in the Zoom. Let's get a 15-minute break. Just go out and drink a cup of water and eat something and go around of your house and talk to someone and come back in, right? It's 1:18, 12 minutes. Okay, 15 minutes. 1:35, right? 1:35. Let's meet at 1:35 to finish the rest, right? Okay. We will check whether we can complete the entire seminar today, or we will complete these parts, and if we need, we will go for another day for the rest, right? We will discuss it later. So go there, go to the outside, just chill and come at 1:35, right? We will start at 1:35. I will post the recording until. Right. Okay. Let's move to the next part of the Vernier caliper. So up to now, we have discussed how to get the least count of a Vernier caliper. So now we are going to read measurements using Vernier caliper. Okay, right. I will again go for my tab because it will be easy to write on the tab screen than the whiteboard in these kind of diagrams when, right? I will again share my screen. Let me share. Right. Hope the screen is visible and I'm audible. Right. Now we are going to take readings from the Vernier Caliper, right? Okay. So I will first draw a diagram here. What's the diagram? Here's the main scale. Here's the main scale, right? So I will also add the values here. Here's the 20, all line millimeters, right? 20, 25, 30, right? Here's the main scale, and the vernier scale is, let's take the vernier scale is here. This is the vernier scale. As you saw before, vernier scale can be slide on the main scale. So the vernier scale, the zero line is here, 0. And then you know that if the zero line is here, for this purpose, I will take the vernier scale, the vernier caliper we were studied at first. The least count is 0.1 millimeters, right? The vernier caliper which was produced by dividing 9 1 millimeter main scale divisions into 10 parts. The earliest one we learned, right? So if the zero mark is here, 1 should be here. 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's the 5. Right. So here's the vernier scale. It's clear, right? So here, what's the reading of this? What's the reading here? What's the reading of this vernier caliper? Here you can say, you can clearly see here, the 0 mark of the vernier scale is coinciding with the 21 millimeter line in the main scale. So it means that initially you can remember that the 0 mark of the main scale was coincide with the 0 mark of the vernier scale. Now it has moved this much, right? Now it has transitioned to this position. So how much the vernier scale has moved here, moved in this direction? How much it has moved? You can simply identify that the vernier scale have moved 21 millimeters up to here, right? It has moved 21 millimeters. So here the reading is the measured length is 21 millimeters, because 21st line of the main scale is coinciding with the 0th line of the vernier scale. Did you get my point? Here the vernier scale means here's the vernier scale. It was initially at 0, like here. Sorry. It was initially at 0, like here. So I have slide it along the main scale. How much? It's 21 millimeters. So if it's 21 millimeters, the 0 line of the vernier scale should coincide with the one line, 21 millimeter line of the Vernier scale, right? Right. Here's the point. Did you get point? So the reading here is 21 millimeters. Complete this. Okay, I will go for the next part also. Now, I'll get a copy of this. I will move this Vernier scale 0.3 millimeters to the right side, right? I'm going to move this Vernier scale in 0.3 millimeters to the right side. So how it appears? You can remember the first things we have learned about the Vernier scales. If I move this 0.1 millimeter, the first line of the Vernier scale should be coinciding with the first line of the main scale, right? Here, you can remember, right? First line of the Vernier scale should be coincide with the main scale line. If I move 0.2, second line of it should be do as that. If I move it 0.3, the third line of the Vernier scale should be coincide with the main scale line. So it should be like this, right? So from here onwards, this is 21 millimeters, 0.1, 0.2, 0.3. Here's the question. Now you can see clearly the third line is coinciding with the main scale division. That means 0.3 millimeters have moved. So I will fine tune the other lines. This should be okay. 4 should be a bit before the 25 line. 4, 5, 6, 7, 8, 9. Yeah, it's fine. So here the coinciding line is this one. We will mark it. So if it shows that the third line, the number 3 line of the Vernier scale is coinciding with the main scale division, you know that this has already slided a distance of 0.3 millimeters. So now the reading is, initially it was 21 millimeters. Initially it was 21 millimeters and now it's 0.3 millimeters. Right? So how does this 0.3 millimeters came? It came as 0.1, the least count into the number of the Vernier line which coincides with the any kind of main scale line. The number of the we only need the number of Vernier scale line. It's 3. This is how the 0.3 was constructed. So we can read any kind of reading using a Vernier caliper by this equation. Reading of the main scale, it's 21. It means the 0th line of the Vernier scale is passes which number? It's 21. It has passed 21. So from the main scale, 21 millimeters are shown. Get my point? Did you get? From the main scale, 21 millimeters are shown because the 0th line of the Vernier scale has passed the 21 line. So the reading of the main scale is 21 millimeters. I will write it below again. It's 21 millimeters plus. Least count of its Vernier caliper is 0.1 into the Vernier scale line that coincides with a line on the main scale. Here we don't want to consider about which line of the main scale. It's useless. We only need which Vernier line. It's third Vernier line. So 0.1 into 3. This should be millimeters. This is the reading. This is how we get a reading from a Vernier caliper, right? Reading of the main scale. So first you have to check which main scale line is passed by the zeroth line of the Vernier scale. It's the reading of the main scale. Plus least count into which Vernier line coincides with the main scale line. Very simple, right? Did you get my point? Complete this. First complete the upper part. Also, if you can do it like this, get a screenshot of the screen, and you can draw it later when you print the tute, right? It's also possible, but work with me simultaneously. Right. Did you complete? Or if you get any screenshot, anything, please put done to the chat. Also write this one. The least count of the Vernier caliper we are considering here is 0.1 millimeters. Okay, put done to the chat if you have completed this, or if you have taken a screenshot or something. Others, what about others? All have to put, right? Otherwise, I can't identify have you finished or not. Quickly put done to the chat. Right. Next. Write this also again under the box. 21 plus 0.1 into 3. Also, we will write the reading. 21 millimeter plus 0.3 millimeters means 21.3 millimeters. Here's the reading. Okay, we will go for these examples. Right, let's do. Very simple, right? Consider the least count of the instrument as 0.1 for these questions. Okay. Here, first one. What's the reading of the main scale? What's the reading of the main scale here? Here, one thing you have to identify. Normally, the main scale is calibrated in centimeters. So here's the 9 centimeter, right? 9 centimeter. So in millimeters, it should be 90 millimeters. This is 9.5. Here you can see in this diagram, you can see this clear, right? One is marked here. That means 1 centimeter. 1.5 is here, and here's the 2 centimeter line. So normally the main scale is marked by centimeters. So here 90. So this should be 89. Like this should be 89, 88, 87, 86, right? This should be 86, huh? Got the point? Okay. The zeroth line of the Vernier scale has passed 86th line. So it means 86 millimeters are given by the main scale plus 0.1 into what is the Vernier scale line which coincides with the main scale line. Let's see. 0, 1, 2. Yeah, here. Here's the line. You can see clear, right? Here's the line. So 0.1 into 2 means the answer 86.2 millimeters. 86.2 millimeters. Very simple, right? Here you can see if the second line is coinciding, the line before the coinciding line is moved a bit forward. and the line after the coinciding line is moved a bit backward, right? Then you can easily identify the which line is coincided with the main scale line, right? Okay, completed, right? Do it with me. For the next, if you want any for further time, or if you have any questions, please let me know, right? Put it in the chat box, or you can unmute yourself and ask. Okay, for the next, it in millimeters, this is 10 millimeters, right? So the zeroth line of the vernier scale has passed 10 millimeter line. So the reading from the main scale is 10 plus 0.1 into which line, which is coinciding? 0, 1, 2, 3, 4, 5, 6. Yeah, sixth line is coinciding with the main scale line. So 0.1 into 6 means 10.6 millimeters. Look how it's easy. 10.6 millimeters. Like after completing every question, the reason for keeping the screen for amount of time is to complete yourself, right? That's why I am even after completing, I keep the screen for few seconds, few minutes to complete it for you, right? Okay, for this question, this is 40, 39, 38 should be here. So from the main scale, it's 38 millimeters plus 0.1 into which line is coinciding? 0, 1, 2, 3. Here's the coinciding line, right? 0, 1, 2, 3. So the answer is 38.3 millimeters. 38.3 millimeters, right? Complete it. If you have completed, go for the next question. Okay, the last question. 5 means here 50 millimeters. This should be 45 millimeters. Then 44, 43, and here this should be 42. So from the main scale, it shows 42 millimeters plus 0.1 into which line is coinciding? 0, 1, 2, 3, 4, 5, 6, 7. Here's the coinciding line, right? Only you want the number of the vernier line, right? 1, 2, 3, 4, 5, 6, 7. 7 is the number. So 0.1 into 7 means 42.7 millimeters. This is the reading of the Vernier Caliper. Complete it also. Okay, now you have a better understanding about how to get a reading using a Vernier Caliper. A nice question. Draw and show how the readings appear on the following Vernier scale. Consider the least count of the instrument is 0.1. 39.3.99 centimeters. First, we will convert this into millimeters. 39.9 millimeters. You have to draw this. How to draw? 39.9 means the main scale reading is 39. We can again break this down into the above formula. This has formed by 39 plus 0.1 into 9, right? Means main scale reading is 39 and the ninth line of the vernier scale should be coinciding with the main scale. So it should be like 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 38, 39, 40. And the vernier scale should be, the vernier 0 should be past the 39th line. It should be here, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right here you can see the 9th line is coinciding with the main scale line, and the line before to that is came a bit forward, and the line after the coinciding line has came a bit backward. That's how you can clearly find which line is coinciding, right? The 9th line. Next one, right? I will give this as a homework, right? At home today itself, draw this and send me a photo. Send me a photo of how this reading is appears on a vernier caliper, which has a least count of 0.1 millimeters, right? I will leave this as a homework. So yeah, here's the Vernier Caliper instrument, right? Here's the Vernier Caliper instrument. Here are the parts of the instrument. You can see these are called internal jaws, right? These two are called external jaws. Means that you are going to measure something external using these external jaws, the external diameter of a cylinder. If you want to measure something internally, you have to put it here, right? Like this, the internal diameter. That's why these two are called internal jaws. These two are called external jaws. And the number 3 is called the rod. Rod is to measure the depth, right? Rod is to measure the depth. Here, you can see how to measure the depth. This amount is measured by this part. Then you can get the reading from here. This depth is the amount of the value of this depth is shown in this what you call in the scale, right? So number 3 is the rod. And also again we can divide this into two as fixed jaw and the sliding jaw. So the fixed jaw means this part. This entire part is called the fixed jaw, right? That's why number 4 is the fixed jaw. This entire part is the sliding jaw. Sliding jaw means the jaw which is able to slide on the fixed jaw. So number 6 is entirely the sliding jaw, number 6. So again, and if you go for the scales, very simple. This is the main scale, this is the vernier scale. So main scale, vernier scale. So what's 8? It's a nut. Nut means you can lock the vernier caliper using this nut. So then you will able to get the reading very easily, right? Otherwise, if you are going to read the reading, while you are reading the reading, the sliding jaw will move and change the reading. So in order to avoid that, there's a lock here. You can you can make this lock and get the reading. That's a simple way how it works, right? So here the least count is 0.1 millimeters. Generally we take the least count of the vernier caliper is 0.1 millimeters, but we know that we can make vernier calipers even even to have a least count of 0.1 millimeters, right? Even to have a least count of 0.05 millimeters. We have done those before, but generally we take it as 0.1 millimeters. Normally the measuring range is 0 to 18 centimeters. Here, so you can see 17 and 18, right? we can use it to measure a range of 0 to 18 centimeters. The minimum length that can be measured without exceeding 1% error, you can remember that I can directly get it by multiplying the least count by 100, right? I'm not going to again work out on the equation. We have worked out on that, not the equation, the inequality for much more times before. So we can get this by easily multiplying the least count by 100. 0.1 into 100 means 1 centimeter. Vernier caliper can, okay, we'll go through this. A vernier caliper can be used to measure the internal length, external length, depth. To measure the internal length, there are internal jaws. To measure the external length, external jaws are there. To measure the depth, rod is there. With the digital vernier caliper, the reading can be obtained directly and it's not affected by zero errors. Nowadays there are digital vernier calipers. You don't want to worry much more about these kind of things to get the reading. In the digital vernier calipers, the reading is shown in the display, right? Very simple, right? Also, it's not affected by zero errors. Until now, we haven't discussed about zero errors. So be patient for that. We will go for zero errors later. A vernier caliper is not suitable for measuring objects that made of soft materials like rubber. This is because the jaws may compress the material, changing its shape and altering the measurement. Right, completely right. Because the object we are going to measure is kept between these jaws. If the object is made up of rubber kind of material, when the jaws are, the jaws can push that material and deform its shape, then the reading will wrong, right? Therefore, for those kind of materials, like the objects made up of those kind of materials, the vernier caliper is not suitable to get the measurements. These are very important point, right? This will be asking the questions. Here, very simple diagrams measuring the external length using a vernier caliper. Here you can see the external diameter is measured. Internal diameter of this cylinder is measured here using the internal jaws. And a depth is measured using the rod, right? Using the rod. Here there's a special point. Zero error does not affect the depth measurement because in measuring depth, the measurement is always taken as a difference between two readings, right? I will explain this again after discussing about the zero errors, right? Here, this is the case. I will go for the whiteboard for you to explain this. Okay, right? This is the last part of the today's session, right? The last part of the today's session about zero errors. What is called by zero errors? Here, this is the zero error of a vernier caliper. When the external jaws are contacting with each other, or the internal jaws are contacting with each other, if the zeroth line of the main scale is not coinciding with the zeroth line of the vernier scale, then it has a zero error, right? When the jaws are contacting each other, means the vernier caliper is fully closed, compacted, fully closed. It should be the vernier scale zero line should be coinciding with the main scale zero line. But when those jaws are contacted in each other, if the scale looks like this, right? This we called as a positive zero error. There's an error in the zero. That's why we called it as zero errors, right? This is called as a positive zero error. And now you can guess this is called as a negative zero error. Positive zero error means a positive distance has pushed to the right side. The Vernier scale has pushed to the right side. It's a positive error. Normally we take this side as negative, so this is a negative error, right? This is what is explained in the zero errors. So how to avoid these zero errors, or how to correct? The correct word is how to correct the zero errors. We can completely correct the zero errors. You can remember, as I explained before, the systematic zero errors are belong to systematic errors, right? At that point, I told that systematic errors can be totally avoided, totally corrected. We are going to correct the zero error. For an example, see this. If we are taking a measurement using a mid ruler, right? Here's the mid ruler. Here's the zero line of the mid ruler. And it goes like this in the scale. And here, let's take it's 35. We are measuring the length of a stick or something like this. What's the length of the stick? What's the length of the stick? Can anyone put on the chat? What the length of this stick? These are in millimeters, right? All are in millimeters. It's fine. So what's the length of this stick? Can anyone put on the chat? What the length of this stick? If I say the length of this stick is 35 millimeters, is it correct? If I say the length of this stick is 35 millimeters, is it correct? No. The reason? Because we haven't starting it measuring from 0. We have started it measuring from 2. So we have to reduce that 2. Means 33 millimeters. This is totally equal to the positive zero error of the Vernier caliper. So if you have a positive zero error, you have to find the error. Here the error of 2 millimeters. You have to find the positive error. Yeah. And reduce that error from the reading. That's it. The next situation. If we are measuring this like this, if we are measuring this like this, if we tell the length of this stick is 35 millimeters, is it correct? Is it correct? No. The reason? The stick is beyond the zero line. So we have to take that part also, right? If this amount is 3 millimeters, if this amount is 3 millimeters, now the length of the stick should be 35 plus 3. Got it? 35 plus 3 means 38 millimeters. That scenario is totally equal to the negative zero error. Means you are start measuring.
एक negative error.
Do you have any question? Right, okay. This means the second scenario means you have a negative error, right? Means you are starting not from 0, you are starting before the 0. So you have to add that part. This is very easy. For positive errors, you have to reduce the amount. For negative errors, you have to add the amount, right? This is the way you should logically think on zero errors. If you can visualize this in any instance that you have to find the zero errors and correct them, if you can visualize this, the example I told you, you never got into wrong in the questions, right? If you can visualize this is a positive error, this is a negative error. Oh, so if a positive error, you are not measuring from 0, you are starting from 2. Then you have to reduce that 2 from the reading, corrected. If a negative error, you are not starting from 0, you are starting before the 0. Let's take, you are starting 3 millimeters before the 0. If the reading is 35, you have to add that 3. It's here. That's the way you have to think logically on this zero error, right? So hands up if you get this point. Hands up if you got my point here. Right, good. Hands up if you got this point. A very simple point, right? If you can visualize this at any time in the exam, if you have this kind of problem, you will never go into wrong. Good, hands up. So that's why I'm always telling you, don't, like, you can't memorize everything in physics until 2 hours, 2 years, right? You have to memorize the things you are learning today up to your exam. It's more than 2 years. How you can memorize one thing for 2 years? That's impossible. The thing you have to do is you have to learn the logic of physics, right? This is the logic here. So I will again go to the tablet. I will go again for the tablet. Let me share my screen. Yeah, you can see my screen. Right. Here, the expression is there. When the external or internal jaws of a vernier caliper touched each other, the zero mark of the main scale does not coincide with the zero mark of the vernier scale. The instrument has a zero error, right? Then the instrument has a zero error. You can't say it other side, right? You can't define it as like when the zero mark of the main scale is coinciding with the zero mark of the vernier scale. If the internal jaws or if there's a gap between internal jaws or external jaws, then there's a zero error. Like that way you can't define, because the reason is if the zero marks are coinciding with each other, if there's a zero error, then there should be a very small gap between these internal jaws or external jaws. From our naked eye, we can't identify these kind of gaps. Therefore, we can't define it, right? Therefore, we can't define the zero error in that way. The only way we can define is when the internal jaws or the external jaws touch with each other, zero mark of the main scale does not coincide with the zero of the vernier scale, then there has a zero error, right? That's the thing. So positive error, how much is the error here? Let's take to calculate the error, it's same as the way you did before, the calculating the readings. So here also you can see the zero mark is past the zero mark of the main scale. So 0 plus. So we don't need to write it. Let's check which line is coinciding. 0, 1, 2, 3, 4. You can see the fourth line is coinciding, right? Fourth line is coinciding. So the reading here is 0.1 into 4 means 0.4 millimeters. Here, there's a small question. You have, okay, first we take the measurement as we did earlier. 0, 1, 2, 3, 4. Sorry, 4. 0, 1, 2, 3, 4. Right. 5. Which one is coinciding? 4 or 5? I think it should be 5, right? This 4 line should be come a bit forward. 4, 5, 6, 7, 8, 9, right? Here's the way. So the coinciding line is 5. If you count it from this side, it is wrong, because we developed that method for when the Vernier scale is going this way. But now the Vernier scale is going to the opposite direction. So you have to count it from this side. So this should be 0. Really, you want to, the real thing you want is, you want to get the length of this part, x. Let's take it as x. You want to measure x. So x is totally equal to this, right? X is totally equal to this. So to get x from here, you have to think that this is the 0th line, this is the first line, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. Then you have to count from this side and get the coincided line. So unfortunately, it's also 5. Then there's no any difference here. But if the coincided line is like 4 from the left side, from the right side, it should be 6. You have always to, if it has a negative error, right? If it has a negative error, the Vernier scale has gone to this side. If it's going to this side, you have to count it from here. It's a simple thing, you can realize it, right? So here, no any problem. 5 into 0.1 millimeters means 0.5 millimeters, right? 5. But in the diagram, you better number it from the right side also, and mark this 5 number. And if you look at the note later, you will realize that you have to count it from the right side if it has a negative error, because you here also always get to know that you can't memorize all these concepts. So here you have to think, if the Vernier scale is going this way, this is the amount it has moved. So to make this amount, you have to think that this is the 0th line, 1, 2, 3, like that. All the things have a logic, right? Here's the positive error and the negative error. So here, as we explained earlier, what should we do to correct this? This should be reduced from the reading. This should be added to the reading. Also, you can remember this like a way like this, right? If you assign plus and minus values for this should be a plus 0.4 millimeter error. Since the right one is negative error, this should be minus 0.5 millimeter error. Also, you can remember this as you always have to reduce the error from the reading. So here, reading minus 0.5. Fine. Reading minus 0.5, it automatically adds the value. You can remember it like this way also. You can remember it like this way. If we are considering positive and negative values for the errors, you can always reduce the error from the reading. So write a sentence here. Write a sentence here. Or after completing everything. After completing everything, write a sentence here like, okay, first complete it. And I assume that you have completed or taken a screenshot or something, right? So right here, you can reduce the error from the reading. You can always reduce the error from the reading. You can always reduce the error from the reading You can always reduce the error from the reading if you are considering errors as plus or minus. If you are considering errors as plus and minus. If you are considering errors as plus and minus. If you are considering errors as plus and minus. If you are considering errors as plus and minus. Okay, for the last part of the today's session, right? I will divide this into 3. Here A is the measurement you have taken. B and C are the 2 vernier calipers which have 0 errors. So they are asking, if the reading A is obtained using vernier calipers B and C, find the corrected value of the measurement. Okay. First we read the measurement here. Here you can see 3 means 30, 31, 32, 33. This is 33, right? 31, 32, 33. So the reading is 33 plus 0.1 into which line is coinciding? 0, 1, 2, 3, 4. Fourth line is coinciding. So 0.1 into 4 means 33.4 millimeters. Sorry. Okay. Here, this has a positive 0 error. First, find the error. Error means 0 plus 0.1 into which line? 1, 2, 3, 4. Fourth line. No? So 0.1 into 4 means 0.4 millimeters. It's a positive 0 error. It's a positive 0 error. To get the corrected value, we have to reduce it, right? Remember the mid rule example. So the corrected value uh, 33.4 minus 0.4 means 33 millimeters. No, we can't say 33.0 millimeters because the 33.0, it should be 33.0 because the least count of the instrument is 0.1. So we have to always report measurements to the nearest 0.1 millimeter, right? The C instrument error. What about the error? This has a negative error. So if it has a negative error, it has gone to this side. If the vernier scale has gone to that left side, the amount it has gone is this one. So to get that one, we have to number the vernier scale from here: 0, 1, 2, 3, 4, 5. Fifth one, right? So fifth line is coinciding from right. So 0.1 into 5. 0.5 millimeters. Since it is negative, we can write it as minus 0.5 millimeters. To get the corrected value, remember the mid rule example, we have to add this value, right? So 33.4 plus 0.5. Here it should be 0.5. Means 33.9 millimeters. This is the corrected value. Right? Complete this. If the reading A was taken from B or C, what are the corrected values? Here are the corrected values. Right? Complete it. Complete everything here and put done to the chat, right? Put done to the chat. After that, we are going to conclude for today. Put done to the chat. put done to the chat after completing. Done. Nice. Done. Okay. I guess everyone has completed, right? The ones who are putting messages have already completed. So then I have to assume that others have also completed because they are not putting messages on the chat is due to they have completed everything. Okay, so fine. I will stop sharing the screen. Right. Okay, listen. So up to now we have completed from the first session we have completed the errors of the measurements, every kind of errors and how to avoid those errors. And now you can you have idea that about the zero error also. And after that we went for the meter ruler and then for the vernier caliper. So from the instruments we have to learn the vernier caliper is the one which has the biggest scope. So we have finished it, completely done. So I guarantee that now you can do any problem, any question related to vernier caliper. So I have to highlight one point. I told that when measuring the depth, right? When measuring the depth using the vernier caliper, you don't want to consider about the zero errors because when we are measuring depth, we always need to take the difference of two readings. Means like this. If we are going to measure the depth of this cylinder, let's take. First, we have to keep the vernier caliper here and get the reading when the rod is touching the top of this vessel. It's R1. And then we have to make the tip of the rod touching the bottom of the vessel, right? Like this, and get the reading again. The way of calculating depth is, the real depth is here, right? H. H means you have to reduce R1 from R2, right? R1 from R2. So then you don't need to consider about the zero errors because you have all your, if there's a zero error, it affects for both R1 and R2 readings. When you get the difference, it will cancel off, right? Therefore, no need to worry on the zero errors when you are measuring depth. The reason why I especially highlighted this point is in the past paper question, in past papers, this have been questioned, right? You have to correct the readings. Out of these readings, there was a one reading that got the depth of a kind of vessel or something. If the student has corrected it also using zero error, it got wrong, right? It gets wrong and you got 0 marks. So you have to memorize that when we are measuring depth, you don't need to get the zero error because you always get it by the difference of two readings. Just can you just have a note there? You can draw these two diagrams and write this and write a point here when measuring depth. The point is there in your tute, right? Point is there in your tute. In the tute also there's enough space. You can draw these two diagrams in the part that they are in the page 16, the bottom of the 16th page, measuring depth using a vernier depth length using a vernier, right? For that part also draw these two diagrams and you can get this equation. By this equation you can realize that the depth is calculated using the difference of two readings. Then the zero error will not affect, even though it affected for both readings and will cancel off when the readings are when we get the difference, right? Complete this. The bottom of the 16th page. Measuring the depth using a vernier caliper. Here, there in the page, there's a sentence as zero error does not affect the depth measurement because in measuring depth, the measurement is always taken as a difference between two readings. That's the thing I have visualized here. Complete this. Complete this. Okay. Complete this and put a message. Finished for today. They are going to finish the session. Complete this and put a message as finished. 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 Okay, good. Finished. Everyone finished. Okay, I assume that everyone finished. Okay, for today, yeah. Okay, thank you. For today, I'm going to conclude from here. The reason is as today is the Good Friday, your Catholic friends wanted to go for the church, and many of them called me, and so I decided to conclude from here for today, and we will have the next part of this session in a later day, right? Later day. And also, if you want to join for the 2028 English medium physics class, you can join it. It starts from 11th April, 7 p.m. to 11 every Sunday, right? From 11th onwards, in every Sunday we have classes at this time, and we are starting mechanics here, right? We are starting mechanics onwards, right? Because from this free seminar we are completing all the measuring instruments part, right? So we are starting mechanics from here onwards, and if you want to join, send me a message as 2028 EM to my number, this, right? 07146543111. Right. That's the point. That's the case. And thank you for joining for today, because if you were not here, I will unable to do the class. Right. So thank you for joining. We will meet at a sooner day to complete the rest of the seminar, and also we will join at the class for the ones who want to join the class, right? Okay, then we will conclude for today. Thank you so much for joining. I will upload the recordings and let your friends know that they can watch the recording and join for the next part of the seminar. Okay, thank you. And also, right. Thank you. I will put all the messages and the things to the WhatsApp group, right? Thank you.